Welcome to today's discussion on problem number 778, swim in rising water.
In this problem, we'll explore an intriguing pathfinding challenge that involves navigating a grid with rising water levels.
We'll break it down step by step, analyze different approaches, and derive an optimal solution.
Let's dive in. In this problem, we are working with an nxn matrix called grid, where each cell represents the elevation of that specific position.
You begin your journey at the top left corner of the grid, which is grid 0, 0, and your goal is to reach the bottom right corner, grid n1, n1. You are allowed to move in 4 directions up, down, left, or right, but there's a catch. You can only move to a neighboring cell if its elevation is less than or equal to the current time t. At the start, time is set to t equals 0, and it gradually increases. Your task is to determine the minimum time t needed to successfully swim from the top left cell to the bottom right cell. The input consists of the grid, which is a 2D array representing the elevation map, while the output is an integer representing the minimum time required to complete the journey.
To understand this problem better, let's go through an example.
Suppose the grid is 0, 2, 1, 3. Initially, you start at grid 0, 0, which has an elevation of 0.
At t equals 0, you cannot move to any neighboring cells because their elevations grid 0, 1, with elevation 2 and grid 1, 0, with elevation 1, are greater than the current time. Once time increases to t equals 1, you can move to grid 1, 0, because its elevation matches the current time. At t equals 2, you can move to grid 0, 1, and finally, at t equals 3, you can reach grid 1, 1. This means the minimum time required to swim from the start to the destination is t equals 3. Now let's look at a more complex example with a larger grid 0, 1, 2, 3, 4, 24, 23, 22, 21, 5, 12, 13, 14, 15, 16, 11, 17, 18, 19, 20, 10, 9, 8, 7, 6. In this case, the minimum time required is t equals 16. At this time, you can traverse the path from the top left to the bottom right corner by swimming through elevations as high as 16. For instance, you might follow the path 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 1, 4, 2, 4, 3, 4, 4, 4. Each step along this path satisfies the condition that the elevation is less than or equal to the current time. This demonstrates how the algorithm must account for elevation constraints when determining the fastest possible route. To solve this problem, there are a few important considerations. First, in the smallest grid size of n equals 1, there's no movement required, and the minimum time is t equals 0. For larger grids, the algorithm must efficiently navigate through potentially large matrices, especially when n equals 50. Elevation differences between adjacent cells can vary significantly, and larger gaps might force the algorithm to wait longer before moving to certain cells, resulting in a higher t-value. Additionally, not all paths are optimal, so the algorithm must identify the path that minimizes the maximum elevation encountered. A priority queue, or min heap, can be used to implement a modified version of Dijkstra's algorithm to achieve this. Alternatively, binary search can be applied to find the smallest t that allows a valid path to exist. These approaches take advantage of the unique properties of the elevation grid to solve the problem efficiently. To begin, let's consider the brute force approach, which relies on exhaustive search. The idea here is to explore all possible paths from the top left corner to the bottom right corner of the grid, calculating the maximum elevation encountered along each path. Once we have these maximum values, the minimum of them becomes our answer. This can be implemented using backtracking or a recursive depth-first search that keeps track of the maximum elevation encountered along the way. However, the problem with this approach is its computational cost. The number of possible paths grows exponentially with the size of the grid, leading to a time complexity of O for n squared in the worst case. While it's conceptually simple, this approach is infeasible for larger grids due to its extreme inefficiency. Now, a more efficient strategy involves using binary search combined with floodfill, either through depth-first or breadth-first search. The key insight here is that we can recast the problem as finding the smallest value t such that we can reach the bottom right corner of the grid without stepping on any cell with an elevation greater than t. To implement this,
we perform a binary search over the range of possible elevations. For each candidate value of t, we use a floodfill algorithm to check if the bottom right cell is reachable. If it is reachable, we adjust our binary search to explore smaller values of t, if not, we explore larger values. This approach is much more efficient than brute force, with a complexity of n squared asterisk log, max underscore elevation. However, it requires careful implementation to ensure that the floodfill process is accurate and efficient. The most optimized approach leverages a min-heap in a way that's similar to Dijkstra's algorithm. Here, the intuition is to use a priority queue to track the cell with the smallest elevation that can be reached. Starting from the top left cell, we propagate to neighboring cells, continually updating the maximum elevation encountered along the path. The solution to the problem is the smallest maximum elevation needed to reach the bottom right cell. To implement this, we initialize the heap with the elevation and coordinates of the top left cell and use a visited set to prevent revisits. At each step, we push the unvisited neighbors of the current cell into the heap, updating the maximum elevation as necessary. The process stops as soon as we reach the bottom right cell. This approach is highly efficient, with a complexity of n squared asterisk log n, since each cell is visited only once, and heap operations are logarithmic in size. By avoiding redundant calculations, this method is both practical and optimal. We chose the min-heap approach for solving this problem because it aligns closely with the core requirements of minimizing the maximum elevation along any path. The use of a priority queue ensures that we always explore the most promising paths first, which is a hallmark of Dijkstra's algorithm. Key insights that led to this choice include the realization that elevation values in the grid can be treated as weights, and the heap structure directly accommodates this. Unlike the binary search combined with floodfill, which requires multiple runs of the floodfill algorithm, the min-heap approach avoids this overhead, offering both computational efficiency and simplicity in implementation. Compared to brute force, which is entirely impractical, and binary search, which adds complexity, the min-heap strategy emerges as the most suitable solution for this problem. While the min-heap approach is highly efficient, it does come with some trade-offs. For instance, it requires additional memory to maintain the priority queue and the visited set. However, these memory requirements are a small price to pay for the significant time savings and the direct alignment of this method with the problem's requirements. In terms of complexity, the time complexity is n squared asterisk log n, driven by the heap operations and the grid traversal, while the space complexity is n squared, due to the heap and visited set. Overall, this approach strikes a balance between efficiency and resource usage, making it the superior choice among the alternatives for tackling this problem effectively. To solve the problem of finding the minimum of the maximum elevations encountered on any path from the top left to the bottom right of a grid, we start by understanding the brute force approach. The grid is represented as a 2D array, where each cell contains its elevation. The goal is to determine a path such that the highest elevation encountered along that path is minimized. Using brute force, we explore all possible paths from the top left to the bottom right. Depth-first search, or DFS, is employed to recursively traverse each path. At every step, we maintain the maximum elevation encountered so far along the current path. Once a path reaches the destination, we record its maximum elevation. Finally, after evaluating all paths, we return the minimum of these maximum elevations, which guarantees the optimal solution. In the brute force approach, we also need to handle edge cases. For grids of size 1 by 1, the solution is straightforward as the single cell's elevation is the result. Additionally, we must ensure that we handle out-of-bound indices and avoid revisiting cells within the same path. The pseudocode demonstrates how to implement this logic. The DFS function checks for invalid paths by returning infinity when encountering out-of-bounds indices or revisited cells. As we traverse, the current path's maximum elevation is updated at each step. If the bottom right cell is reached, the function returns the current maximum elevation. To explore all possible directions, we iterate through the 4 cardinal directions: right, down, left, and up. As the DFS progresses, the minimum result is updated with the smallest maximum elevation from all valid paths. After exploring all directions, we backtrack by unmarking the current cell in the visited matrix, allowing it to be used again in other paths.
The DFS function then returns the smallest maximum elevation found during its recursive exploration. The main function, min_max_elevation, initializes the visited matrix and starts the DFS from the top left corner. This brute force approach ensures that every path is considered, guaranteeing correctness. The algorithm revolves around tracking the maximum elevation along each path. By the end of the traversal, we will have the smallest maximum elevation among all paths, which represents the optimal solution. The algorithm works by minimizing the maximum elevation across all paths. The visited matrix plays a key role in ensuring that cells are only used once per path, while backtracking allows us to reset the state for exploring alternative paths. The main data structures involved include the grid, which stores the input elevations, the visited matrix, which prevents cycles and redundant computations, and the recursive stack, which is used by the DFS to traverse paths. These components together enable systematic exploration of all possibilities. However, due to the exhaustive nature of the brute force approach, the algorithm can become computationally expensive as the grid size increases. The time complexity of this approach is exponential, specifically O for caret, n*n, due to the sheer number of paths explored in the worst case. The space complexity is dominated by the recursion stack and the visited matrix, both of which are O(n²). To optimize this brute force method, we can introduce techniques like pruning, where paths with a maximum elevation already greater than the current minimum are terminated early. This avoids unnecessary computation. Additionally, memoization can be used to store results for specific states, such as the combination of grid position and current maximum elevation, to prevent redundant calculations. These optimizations can significantly reduce the computational overhead and improve the efficiency of the algorithm. To solve the swim in rising water problem, we start by importing the necessary tools and setting up the solution class. The key idea here is to use a min heap, which helps us prioritize the next cell with the smallest elevation. We define the grid size and the possible movement directions, right, down, left, and up. The heap is initialized with the starting cell, located at the top left corner, along with its elevation. We also create a visited set to keep track of cells we've already processed, ensuring we don't revisit them. The variable max_elevation will store the highest elevation encountered along our path, as this will determine the minimum time required to reach the bottom right corner of the grid. Inside the while loop, we extract the cell with the smallest elevation using heap_pop and update max_elevation accordingly. If the current cell is the bottom right corner, we've reached our destination and can return max_elevation as the result. Otherwise, we proceed to explore all valid neighboring cells. For each neighbor, we calculate its coordinates and check if it lies within the grid boundaries and hasn't been visited yet. If the neighbor is valid, we mark it as visited and push it into the heap along with its elevation. This ensures that the heap always contains the next possible cells to process, prioritized by their elevation. By repeatedly extracting the smallest elevation and exploring neighbors, we can incrementally find the optimal path to the bottom right corner of the grid while tracking the maximum elevation along the way. This completes the implementation of the algorithm, ensuring an efficient solution to the problem using a combination of a min-heap and a breadth-first search approach. Here, we start by importing the necessary utility classes and defining our solution class. The method swim in water takes a 2D grid as input, where each cell represents the elevation at that point. First, we determine the size of the grid, n, and define the possible movement directions, right, down, left, and up. These directions will help us explore neighboring cells later. Next, we set up a priority queue, or min-heap, which will allow us to process cells based on their elevation in ascending order. We begin by adding the starting cell at the top left corner, with its elevation and coordinates. To track visited cells and prevent revisiting, we initialize a Boolean matrix visited and mark the starting cell as true. We also define a variable max elevation to keep track of the highest elevation we encounter along the path. Then, we enter a while loop that continues processing cells until the heap is empty. Inside the loop, we retrieve the cell with the smallest elevation, update max elevation to ensure it reflects the highest elevation we've stepped on so far, and check if we've reached the bottom right corner of the grid. If we have, we return max elevation, as it represents the minimum time required to swim across the grid.
Next, we explore the neighboring cells of the current cell by iterating through all possible directions. For each direction, we calculate the coordinates of the neighboring cell and check if it's within the grid boundaries and hasn't been visited yet. If these conditions are met, we mark the neighbor as visited and add it to the min heap along with its elevation and coordinates. This ensures that the cell will eventually be processed in the order of its elevation, maintaining the priority queue's purpose. The while loop continues this process, exploring new cells and updating the maximum elevation encountered until we either reach the bottom right corner or exhaust all possibilities, though the latter is impossible in a valid grid. Finally, the method includes a return statement of -1 as a safeguard, but this line is unreachable because the problem guarantees a solution exists. This implementation efficiently combines the use of a priority queue and breadth-first search to solve the problem with optimal time complexity. Here, we are given a small 2x2 grid. Our goal is to determine the minimum time required to swim from the top left cell to the bottom right cell while navigating through rising water levels. To solve this, we use a priority queue or min heap to simulate the process. The heap is initialized with the starting cell, 0, 0, at elevation 0. We also maintain a set to track visited cells and initialize max_elevation to 0 to keep track of the highest elevation encountered so far. Now, in the first iteration, we process the starting cell, 0, 0. After popping it from the heap, we explore its neighbors, moving right to 0, 1, with elevation 2 and down to 1, 0, with elevation 1. Both neighbors are added to the heap and marked as visited. At this point, the heap contains two entries, 1, 1, 0, and 2, 0, 1. Next, we process the cell, 1, 0, from the heap, which has the lowest elevation among the remaining cells. The max_elevation is updated to 1, as this is the highest elevation encountered so far. Then we explore its neighbors. Moving right to 1, 1, with elevation 3, we add this cell to the heap and mark it as visited. The heap now contains 2, 0, 1, and 3, 1, 1. In the third iteration, we process the cell 0, 1 with elevation 2, updating max_elevation to 2. Finally, in the fourth iteration, the cell 1, 1 is processed. This is the bottom right cell, and its elevation 3 becomes the final max_elevation. Therefore, the output for this grid is 3. Now, we look at a slightly larger 3x3 grid. The approach remains the same: use a min heap to prioritize cells with lower elevations, update the max_elevation as we traverse, and track visited cells to avoid revisiting. Starting with cell 0, 0 at elevation 0, we incrementally process cells in the order of their elevation. For this grid, the traversal order includes cells such as 0, 0, 0, 1, 0, 2, 1, 2, and so on, eventually reaching the bottom right cell, 2, 2, at elevation 8. The max_elevation is updated step by step as we explore higher elevation cells. By the time we reach 2, 2, the maximum elevation encountered along any valid path is 8. Thus, the output for this grid is 8. In the third example, we have a more challenging 3x3 grid with varying elevations, including obstacles. As before, we initialize the heap with the starting cell, 0, 0, at elevation 0, mark it as visited, and set max_elevation to 0. The traversal order depends on the elevations of neighboring cells. Here, cells such as 1, 0, and 0, 1 are processed early due to their lower elevation, but moving to cells like 1, 1, with elevation 8 significantly increases the max_elevation. This higher elevation temporarily slows the path, but we continue exploring until reaching the bottom right cell, 2, 2. Ultimately, the maximum elevation encountered along the path is 8, making it the output for this case. To analyze the time complexity of our algorithm, we begin by considering the operations performed by the priority queue, which is implemented as a min heap. In the worst case, every cell in the nxn grid will be pushed into the heap exactly once. Since the grid has n-2 cells, this results in n² push operations. Each push or pop operation on the heap takes logarithmic time in relation to the number of elements in the heap. When the heap contains all the grid's n-2 cells, each operation takes log n², which simplifies to log n. Therefore, the total time for all heap operations is n² *log n. Additionally, we have neighbor exploration. For each cell, we explore up to 4 neighbors, which is a constant amount of work per cell. With n-2 cells in the grid, the total work for neighbor exploration is O(n squared). When we combine these, the overall time complexity is dominated by the heap operations, resulting in O(n squared * log n). Now let's analyze the space complexity of the algorithm, which is influenced by several factors. First, the heap itself can store at most all n-2 cells of the grid, so the space used by the heap is O(n squared). Second, we maintain a visited set to ensure that each cell is processed only once. This set can also contain up to n-2 entries, requiring O(n squared) additional space. Lastly, the input grid is already provided and occupies O(n squared) space. When we add these together, the total space complexity is O(n squared), as the dominant factor is the size of the grid and the data structures used to track progress. Let's consider how the algorithm performs in different scenarios. In the best case, the algorithm processes the shortest path through the grid. However, even in this scenario, cells still need to be pushed into the heap, leaving the time complexity at O(n squared * log n). For the average case, it's reasonable to assume that most or all cells are pushed into the heap, so the time complexity remains O(n squared * log n). In the worst case, the algorithm must explore every cell in the grid, which also results in O(n squared * log n). To highlight the efficiency of the current solution, compare it to a brute force or naive approach. A naive algorithm might explore all possible paths, leading to an exponential time complexity of O(n squared), as each cell has up to 4 neighbors and the exploration involves extensive backtracking. This is infeasible for large grids. By contrast, our optimized solution, which processes cells in order of elevation using the priority queue, reduces the problem to O(n squared * log n, making it exponentially faster. Finally, let's solidify our understanding of the algorithm's efficiency with a proof of its big O complexity. The priority queue is the cornerstone of the algorithm's performance. By always expanding the cell with the lowest elevation, we ensure efficient progress toward the solution. Each cell in the nxn grid is processed exactly once, resulting in O(n squared) operations. Since each operation requires a logarithmic adjustment to the heap, the overall time complexity becomes O(n squared * log n). Similarly, the space complexity is driven by the size of the heap and the visited set, both of which scale with the number of cells in the grid. This leads to a space complexity of O(n squared). Together, these factors highlight the efficiency and scalability of the algorithm. When tackling this problem, there are a few common mistakes that can trip you up. First, forgetting to account for edge cases is a frequent issue. For example, small grids like 1x1 or 2x2, or grids where all values are the same, need to be handled explicitly to avoid incorrect results. This often happens because algorithms might assume a minimum grid size or variability, leading to out-of-bounds errors or flawed logic. Another mistake is misinterpreting the problem constraints. A common misunderstanding is to focus on minimizing elevation differences rather than considering the minimum of the maximum elevations along the path. This misinterpretation can lead you to develop a completely irrelevant approach, often resulting in a slower solution with a higher time complexity, like O(n squared), when an efficient O(n log n) solution is possible. Finally, relying on inefficient brute force methods without optimizations, such as memoization or pruning, can make your solution too slow, especially for larger grids where the size approaches 10,000. This often leads to exceeding time limits during execution. Now, another pitfall to avoid is hard-coding assumptions about the grid layout. For example, assuming the grid is always square or that certain paths, like diagonals, are guaranteed can create major issues. This reduces the generality of your solution and may cause it to fail on test cases with unexpected grid dimensions. Additionally, if you're using a priority queue, which is common in efficient solutions, you need to pay close attention to edge cases. Failing to properly update visited nodes or allowing duplicate entries in the heap can lead to subtle bugs, such as infinite loops or incorrect path calculations. These issues can be particularly challenging to debug and might cause your solution to fail specific test cases. Proper handling of the heap and visited nodes is crucial to ensure both correctness and efficiency. This problem is a great opportunity to demonstrate your ability to balance brute force and optimization. While a naive DFS or BFS may handle small grids, larger inputs demand more advanced techniques, such as binary search on the elevation range or using a heap-based Dijkstra's algorithm. Recognizing this trade-off is a key insight interviewers look for. Additionally, this problem falls into a common category of grid-based pathfinding problems. Mastering algorithms like BFS, Dijkstra, and dynamic programming on grids is essential for tackling similar challenges. Interviewers will also test your awareness of complexity trade-offs. For instance, can you optimize a brute force O(n) squared solution into something more efficient, like O(n log n) or O(n log max underscore value? Highlighting these trade-offs, such as time versus memory usage, can set you apart. Finally, clear communication is vital. Make sure you explain why you're choosing a specific strategy and acknowledge its limitations. For practice, related problems like LeetCode 1631, path with minimum effort, or LeetCode 743, network delay time, can help solidify these concepts. There are several approaches to solving this problem, each with its own trade-offs. A brute force method using DFS or BFS is simple to implement but inefficient for large grids. Its complexity can reach O(n) squared for traversal, with an additional O(n) for checking the maximum elevation. A more optimized approach is binary search on the answer combined with BFS or DFS. This reduces the problem to O(n log max underscore value by narrowing down the elevation range, although it's more complex to implement. Another commonly used method is Dijkstra's algorithm, which is a heap-based BFS. This approach is optimal for shortest path problems with weights and has a complexity of O(n log n). However, it requires careful handling of visited nodes and heap updates to avoid bugs. Lastly, dynamic programming can work for simpler problem variants, but it may not scale well for unrestricted pathfinding with elevation constraints. Each method has its strengths and weaknesses, so understanding when and why to use them is crucial for mastering this problem. To wrap up, we reviewed the problem swim in rising water and its optimal solution using a priority queue. We discussed key takeaways, including the importance of graph traversal techniques and efficient data structures like min-heaps. Thanks for joining, and don't forget to like, subscribe, and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!